I'm really glad to invite you to work in my lab. So basically, it's a radiation detector R&D lab. So when we talk about radiation, we always think about the nuclear power plant or the X-ray, the CT machines. However, actually, radiation is in our life, in our environment, everywhere. So the most common one is the cosmic ray radiation. So when the high energy cosmic ray strikes the atmosphere, it will create a shower, and actually it will develop, becomes bigger and bigger. However, after a certain depth, it will be absorbed by the atmosphere again. So if you take an airplane, actually you are going to have more radiation than if you stay on ground. So here is a plot showing you the flux of the radiation. The yellow line is what you are going to get on ground. So this is what you are going to get in a plane flying high, and if the plane gets lower, you are going to have less. So it's obvious that don't take plane too often. I'm just joking. And another one is radon. Radon is a gas. So actually, it is emitted from the soil everywhere. So if you have a basement at home and you do not ventilate very often, then actually radon will accumulate in that place. So if you go there, it's actually not good for your health. This is also an issue for the mining companies. The miners, they go to deep underground there, actually they have this issue of radon. If they smoke in the mine, actually they have a big issue for their lungs. So here is the concentration of radon in this country. This is a zoom in of South Dakota. You can see that we are in the red zone. So another common radiation is actually from the food. Bananas contains potassium, and potassium 40 is a natural existing radiation source, radiation isotope. So if you actually put a banana close to a radiation detector, you can see it. I've done that when I was a PhD student in an open house show. We have a germanium detector there, and then we put a bunch of bananas close to it. Then you can really see the potassium 40 lines in your spectrum. Here is a careful calculation telling you that this will not cause any health problem for you. So don't worry too much about it. However, you need to recognize that radiation is everywhere. Actually, if you're sweating, in your sweat there is potassium 40. So in the low background canning facilities, if you use your bare hand or if you're sweating there, actually that will cause problem for the low background canning facility because you are contributing potassium 40 there. So to detect the radiation, we always say that once a radiation strikes your detector, it will create either sound or light or electricities. That's a fancy way to say it. Actually, that's a way to help people to understand it. So basically, it will create ionizations. So if you apply high voltage, you can extract the ionization signal from the detector, or it will create scintillation light. Then you are going to need a light detector. Basically, it's a photon multiplier, where here you have a piece of material. So this one will create this photoelectric effect easily. So you are going to get electrons when a light is striking this piece of material. And then this electron will be so this electron will strike another piece of metal and create more electrons there, and more and more and more and more, and finally you are going to have a visible electronic signal. Another one is sound. Actually, it's a phono. So you are going to create the vibration of the atoms in your detecting material. That will increase the temperature temporarily in your detector. So you can detect that change of the temperature using some temperature sensors. So these are like 3 common ways to detect the radiation. And we are going to concentrate the first 2. So we are going to use germanium detector, which will detect the ionization in the germanium crystal. So this kind of detectors can have different configurations. For example, it can have a very simple one, that is just a block of germanium detector. You apply voltage on this side and that side, and then you create an electric field this way. And then if you have ionization inside, the ionization will drift towards 2 different panels, and you're going to detect them. Or you actually have a cylindrical shape, and then you create so you apply high voltage in the core or to the outside, and then you create this kind of electric field. But the basic principle is the same. The problem is that you have to operate germanium detector in a very low temperature. Otherwise, the electrons are too easy, are too hot. I mean, the temperature is too high. The electrons moving freely in the a lot of electrons can move freely in the crystal. That creates a huge amount of current, which is not good to operate this type of detector. So you need to cool it down so that not all the electrons are moving freely there. So you need cryogenic system. So normally we use liquid nitrogen here. So you have a copper bar connecting your detector and liquid nitrogen, so that your detector can be cooled down. So normally when you involve low temperature, you have to involve vacuum at the same time. Because if you do not involve vacuum, then your detector will be warmed up by the environment immediately. So you have to involve liquid nitrogen, vacuum, and high voltage. The high voltage is used to extract the ionization signals from the detector. Another one we're going to use is the sodium iodide and the cesium iodide. They are scintillators. Basically, if you have radiation strike those kind of crystals, they will create a scintillation light. And then we're going to use the light sensor. Basically, it's a photomultiplier tubes to detect those light. So here are the examples of the pictures of these crystals. They look really beautiful. So actually, the blue light are the typical scintillation lights created, emitted from them. Actually, most of the light are in the UV range, that's ultraviolet range. Actually, you cannot see it in your eye, but you can see the edge of the emitting spectrum. That's blue lights. And this type of scintillator has a big problem. That is, it absorbs water easily. So this is a good one, and this is the one that absorbs too much water inside. So in order to operate this type of detector, you have to assemble everything in an environment where the humidity is really low. So normally the relative humidity in this room is about 40%. But in order to operate this type of detector, you need a humidity down to 3%. So how can we do that? You cannot survive in such kind of heat. So in order to create that 3% relevant humidity. One way is to flush is encapsulated space with nitrogen gas. Just get rid of all the water vapors in the air. However, a human being cannot work in that environment. So what we are going to do is that we create a glove box, and we put all the equipment inside, and then we flush the glove box with nitrogen, and we see whether we put a humidity sensor there, and see if it can drop down to 3%, and then we can operate it there. So we need a cryostat, obviously, and the cryostat we are going to use is going to be different from the one you always see for traditional germanium detector. We are not going to use any cooling finger here to connecting the detector and the liquid nitrogen. What we are going to do is that we create a vacuum chamber like this one, and we'll put our detector in the chamber, and then we dump the whole thing into liquid nitrogen. So we just cool down the whole thing. Not just a single bar there. So once you put this type of chamber in open door, you pour liquid nitrogen in to cool the whole thing down. So here are some pictures showing you how a piece of sodium iodide is mounted at the bottom of this chamber, and then on top of it, a photomultiplier tube is mounted, and then cables are wired up, so you can read out from here. And then the whole chamber can be pumped to vacuum, and then flushed with nitrogen gas, so that you can cool down the whole thing efficiently. Without a gas inside, you really rely on the radiation to cool down the whole thing. With gas inside, you rely on the bumping of the gas atom inside to cool down the detector. So we need glove box to assemble the detector inside. So we need nitrogen gas. So we have to connect the nitrogen bottom with our glove box and flush the whole thing. So I summarize some of the projects related to those detector development. First one is assemble the cryostat with a limited amount of designing effort. So go back here. I already purchased most of the part of this cryostat. You need to put everything together. Something is missing inside. You need to figure out how to finish the whole thing. If you need any money, just talk to me, and I can purchase that for you. And then we need to design and build a mounting structure for holding the detectors in the cryostat. We need to assemble the glove box, and we need to assemble coaxial cables, and to use these cables to read out signals from our detector in the cryostat. There is another project for you, that is to measure the speed of light in those cables. We already measured the speed of light in the air. And this time we're going to measure the speed of light in the cable. Another thing is to design and build an LED driving circuit to calibrate PMTs. So those light sensors, they need to be, their properties has to be studied before we use them. We normally use the LEDs to study it. So we need to control the intensity of the LEDs. So this is another project. We can also write programs to record the digital waveforms from a fast oscilloscope. So everything, all the electronic signals will be recorded by the oscilloscope. We don't like to save those signals into a PC, so we need some programming to do that. Another one is to design a web page and to create channels in social media site, for example YouTube. If I record this one, I put it in in YouTube. And if you are doing something like create a glove box, you can film the whole process and put it on YouTube and tell people how to do that. And show people your design. So a bit more details about each project. The cryostat, what you are going to learn is the industrial standard of a cryostat, like the CF, KF flanges. That is the thing you use to close the chamber. And the swage lock fittings, like a lot of pipes. It's like a plumbing job, but in scientific area. And then you need to fit in the high voltage signal and the gas into or out of your chamber. So you need those fit-throughs. You need to learn how to connect those fit-throughs into the chamber. And you have to learn the cleaning, assembling, and pumping, filling, and cooling procedures of operating this type of cryostat. And then you need to learn to handle high-pressure gas. For the mounting structure, you are going to learn how to assemble germanium and scintillation detectors with PMTs and electronics in a cryostat. And you need to monitor the temperature profile of the whole setup. And you need to learn how to block the infrared radiation from the warm part of your cryostat. You know, Nazil just wrote a master thesis talking about his attempt to construct a cryostat to run the germanium detector. I believe you can do it too. Right now, you don't need to have a master degree to do this. We can do it in this class. We can set up the whole cryostat and then put down the detector in it. And for the glove box, I searched on Google. The standard ones is more than $1,000. Like this one, it's really, really small. You see the door here. You can put this in. Once you assemble the whole thing, you cannot get it out. It's just too small, and it's overkilling. So they have many setups here, but we don't need it. So if you check the homemade ones, actually there are many videos in YouTube telling you how to make a glove box. They are cheaper, and you can make it bigger, and it meets all your needs. So it's perfect. So what we are going to do is that we are going to create one by ourselves. So the standard ones are actually acrylic panels glued together, but we are going to use the frame called 80-20 frames. So I bought all of them. It's basically plug and play. You can put them together, and I already bought the acrylic panels. You need to put everything together. However, you have to drill holes in an acrylic panel to create holes like this. And you need to buy gloves, and you need to glue. I also bought acrylic tubes like this. You need to glue this on your glove box so that you can mount your gloves there. And then on top of your glove box, you're going to drill small holes so that you can fit in nitrogen gas into it to flush the whole thing. And the bottom of this glove box should be open so that you can raise the whole thing and put everything down there and close it. So you have to fit, and also you need to put electricities like a socket, like how do you call that?
No.
Extension.
Okay.
Yeah. You need to put a socket in the glove box so that you can use some electricity inside. You have electricity inside. And then you need to seal the whole thing, the bottom of it, so that there's no leak. But you need to open it easily. So it's better to have some kind of tape there, very soft, rubber tape. Once you put the whole thing down there, the weight of it will seal the whole thing automatically. So this involves a little bit design. I bought already almost everything, but you have to do a little bit design yourself. If you need anything, just tell me, I can buy it for you. Then the coaxial cable and the speed of light. So what we're going to learn is to prepare coaxial cable. The coax is short term for coaxial cable. For standard connectors, we are going to connect the BNC, this is safety high voltage connector, whatever, to your cable, and then you can use those connectors to connect to a function generator and oscilloscopes. So we are going to connect a function generator with a oscilloscope, with a short cable and a long cable. So we are going to generate a square pulse from the function generator and split it, and send it through two cables. You are going to see that the same signal will arrive your oscilloscope at different time, and then you can measure the time difference. Actually, it's a really, really tiny nanosecond or something. However, this oscilloscope is a really fast one. It can resolve nanosecond difference. So you can use this oscilloscope to measure. If you measure the length of the cable and measure the time difference of this signal, you're going to measure the speed of light in the cable. For the LED drive, again, we're going to have LEDs. Those LEDs emit ultraviolet light. They have to be used in vacuum or nitrogen gas to avoid creating ozone. So if you just operate ultraviolet LED in a normal environment, you are going to create ozone. Actually, this is the way how the atmosphere protects us from the ultraviolet from the sun. The atmosphere absorbs a lot of ultraviolet radiation from the sun. That's why we are safe. But that's why there are a layer of ozone in the atmosphere. So the LEDs has to be put in the vacuum chamber, and we have some feed-throughs you can connect cable. That's why we need those coaxial cables. And then you have to develop a simple circuit so that you can tune the intensity of the LED. So you can have intensity in all levels. The more precise, the better. I forgot to mention, the reason we need this UV LED is because it simulates the scintillation light from the scintillation crystals. The oscilloscope, so I bought a really fast one. As far as I know, this should be the fastest in our department, and it's very expensive. We're going to use it as a DAQ system, that is a data acquisition system, to record very fast scintillation light signals from our detector. So we need somebody to write a program in the computer so that we can save those fast signals from the oscilloscope to a PC. And about web page and social media channels, what we are going to do is to should be recorded in the form of digital lab logs. We've already done that, so you know how to do it. Actually, let me show this later. So we can also take videos and upload it into YouTube. And then we are going to have a web page, a central web page that have all the related channels linked. So we got support from this activity from the Center of Teaching and Learning. So I bought many things for this project. So iPad mini with the case, the armor case, so you can drop it on the ground, and then you can mount the iPad here and mount it on the nanny tripod. And then you have this tripod, so that you can mount it in any kind of bars. And with this, you can mount your smartphone on it, so take videos. And here I have digital pens. You can write directly on the screen of iPad mini. So to create a digital lab log. And this is the Bluetooth keyboard, so that you can type. If you don't want to write, you can type. So we got many gadgets here. And the requirements, before you do all of this, you have to pass some safety trainings. So this is a required. There is electrical safety, pressure safety, high voltage safety, and mechanical safety. At first, everybody has to pass the electrical safety. This is standard. It takes about half an hour. After you, so in this web page, they have just pages of slides. You need to spend half an hour to read them, and then after this training, you have to take a short quiz, and then you have to email me the result of this quiz. You have to pass it, and I need to save your result in case there's any accident. I need to show this so that you can be covered. Otherwise, we are going to have a problem. And if you choose to do some nitrogen-related project, you have to pass this pressure safety. And if you want to operate the detector, you have to pass the high voltage safety test. And then, when construct the chamber, you actually have to use some solvent to clean the chamber. So any high vacuum chamber has to be cleaned before pump it. So in that case, you need to pass the chemical safety. You don't need to pass all of this one in one day. Just do it right before you do the required, the related activities. And then we are required to take videos to record everything we've done. This is because we apply for that fund, so we have to, have to do this.